We're going to start dividing polynomials. It does help if you already know how to divide regular numbers, because we're going to divide polynomials using long division. So again, if you forgot how to divide regular numbers, you might want to pause, check how to divide regular numbers using long division without a calculator, and then um, come back and perhaps do this. That is not necessary, but it does help. Okay. Um, the first thing we notice, this is the first example when we are dividing polynomials, is that there's going to be a process. We're going to find something that multiplied with x squared gives us x to the 4. And of course, that is going to be x squared. Actually, let me start and tell you why this process is initially going to fail, and then we're going to fix the failure. Okay, so let's start this problem. I want to figure out something that multiplied with x squared gives us x to the 4. And of course, that has to be x squared. X squared times x squared is x to the 4. And we multiply that out, x to the 4. Okay, and then we follow through. X squared times 2x is 2x cubed. So we do plus 2x cubed. And here's the problem. X squared times 3 is 3x squared, but there is no place to put the x squared. See, this is the column of x's to the 4, column of x's to the 3, column of x's and column of numbers without x's. But there is no x squared to put the x squared, the 3x squared of the multiplication of x squared with this. So there is none. So here we have a problem. And some of the problems in the homework are going to be like this. So pay close attention to that, because that can mess things up, especially once we start working with synthetic division. So right off the bat, I'm telling you, there's going to be problems in quizzes and tests where something weird like this is happening. Well, it's not that weird, but something like this is happening where the x squared is missing. And if we know how to handle that situation, your answer is going to be wrong. And if we have a multiple choice problem, I'm probably going to come up with the wrong answer, in which we don't put the 0x squared here. Okay, so just pay close attention to that issue. Okay, so what is the problem? There is no column of x squared, and so there's no place to put these 3. Excuse me, this 3x squared. Boy, this is the second time that the whole day, I'm not sneezing. The entire day. When do I sneeze? When I'm recording. Isn't that funny? X to the 4 minus 2x cubed. We're going to put 0x squared. Pretty much, there's a few times when we do this, when we put 0, because we want to put a column for the x squareds. And as written up here, there isn't one. So that is a problem. So we're going to redo this. X squared plus 2x plus 3. And the only difference is that now we have a spot for the x squared. See, when you have regular numbers, this is just out of the blue, like 705. You consider this out of the blue, just off example. 705, we put a 0 there because there's no tenths. There's 700, no tenths, 5 units. So this 0 is telling us that there's no tenths. With polynomials, we don't have to do that. In fact, we encourage not to do that, not to put zeros, because putting a 0 is really useless, because if you don't see it, then there isn't any. It's not like this. In here, we have to put the 0, because if we write 75 or 75, that's not the same thing as 705. And even if you put a space, 7, 5, that looks actually kind of weird. Is that a 7 and a 5, or what? You know, if we want to put 705, we have to put a 0, because the position of the number has something to do with the value of the number. The position of where the x squared is, or the x or the x cubed is not that relevant. As long as it is present, we don't really care. We can always rearrange polynomials. So that's why with polynomials, if you are missing um, a term, we don't write it down. If we don't put 0. However, in some instances, such as in division, we do here in the dividend, because we need the column. Okay, so now let's go ahead and work through this. So x squared times x squared is x to the 4. X squared times 2x is 2x cubed. X squared times 3 is 3x squared. See, now there is a spot, a column that x squared belongs to. Up here, there wasn't one. You could argue, well, can we put it here? You can put it somewhere else, but that kind of messes up the problem. Okay. And then we subtract. Now, this is exactly what happens when we do long division of regular numbers. We subtract. Just to give an example, let me do a quick example. Let's say you have 705, and we want to divide this by, I don't know, 4. Okay, so how do we do that? Figure out how many times 4 fits into 7. Well, it is 1 time. And then we multiply and we get 4. And then we subtract. 1 times 4 is 4, and then subtract, you get 305. We bring down those numbers. Does 4 go into 3? No. Does 4 go into 30? Yes. 7 times. 7 times 4 is 28. And then we subtract, and then we end up with 2 and 5. And then we think, okay, does 4 go into 25? Yep. How many times? 6. 6 times 4 is 24. So I'm going to move the 25 over here, 25. So 24, and then we subtract, and we have 1 left over. So 605 is the same thing as 176 times 4 plus 1. That's so, whoa, that came fast. 705 equals 4 times 176 plus 1. Or the other way to put it is 705 over 4 equals 176. But then there is 1/4 left over, or one unit in the division, which is equivalent to 1/4. So please review this if you don't remember. It's easy to forget. But the reason why I was bringing that up is because there is a subtraction, and the subtraction is the same as the subtraction when we do regular long division. Yeah. So subtract, and then we have x squared minus x squared, no x squared. So that's going to be nothing. We don't put anything down. And here we got to be careful. Negative 2x cubed minus 2x cubed. So we have negative 2 minus 2. That puts us at negative 4x cubed. 0 minus 3. Negative 3x squared. And then what I do is I bring down the other terms because oftentimes we forget. You could leave them there and then keep subtracting. But then oftentimes I forget that they're there. So I just bring them down to this line. So now I don't have to think whether there was going to be something that is behind that I had to worry about. Okay. Now I need something that multiplied with x squared that will give us negative 4x cubed. Well, that has to be negative 4 to match the negative 4, and an x to match the x cubed because we already have x squared. And then we multiply through. Negative 4x times x squared, negative 4x cubed. Negative 4x times 2x, negative 8x squared. Negative 4x times 3, negative 12x. And we subtract. Now watch out, because there's going to be a few double negatives that we have to worry about, or kind of 3 negatives involved. So negative 4 of those, double negative, that makes it a plus. So negative 4 plus 4 is 0. So this guy vanishes, this cubes vanish, which is the whole point. We want to knock down the degree of the polynomial one by one. So we knock down the x to the 4. Now we're about to knock down the x cubed. Well, we did. Let's finish this up. So negative 3, double negative, so that is plus 8. So negative 3 plus 8 is 5x squared. Negative 11 plus 12, that means plus 1x plus 36. Okay, so the x to the 4 is gone. The x cubed is gone. By the way, it's not that the 2 is gone. As a consequence of knocking the x to the 4 down, we have to change the 2x cubed into 4, negative 4x cubed. As a consequence of knocking down this next term changed from negative 2 to negative 4. But that's okay. We knock it down. As a consequence of that, this negative 3 becomes positive 5x squared. And then we knock this one down next. So we add 5, because 5 times x squared is going to match this 5x squared, and then when we subtract, when it is the time to subtract, those two are going to go away. I'm getting ahead of myself because I already put the parenthesis and the negative and the line, but we still have to multiply more terms. 5 times 2x is 10x. 5 times 3 is 15. But mind, all of this quantity, all of this polynomial is going to be subtracted from that polynomial. So 5 minus 5 is 0. 1 minus 10 is negative 9. 36 minus 15, 21. Plus, oh, I missed the x here, negative 9x plus, oh, that looks really bad. Okay, negative 9x plus 21. Okay, so the guy inside the box is called a dividend. This is the quotient. This is the divisor. Oh, sorry, quotient. Maybe you couldn't see that on the screen before. Quotient, divisor. The stuff inside the box is the dividend. And this is called the remainder. Not to be confused with reminder. Yeah. Anyway, now, why don't we continue? We don't continue because the degree of this polynomial is 1, which is smaller than the degree of this polynomial, which is 2. So the size of a polynomial is given by the degree of the polynomial. So let's talk about size for a moment. The, in quotation marks, size of a polynomial is given by its degree. Degree, and what do we mean by degree? Degree is the largest exponent of a variable. If a polynomial of degree 1, rather of degree of one variable. So degree means the largest exponent. So for instance, just to give a sub-example, compare 1000x versus half x squared. Which one is bigger? This one is bigger because the degree is 2. The degree of this guy, which we never write down, is 1. So x to the 1 versus x. Never mind that this is 1000, which is huge compared to the 1/2. But x squared is what matters in this case, not the 1000. So the coefficient is not that important. What is important is the exponent. So this polynomial has degree 2. This polynomial has degree 1. That one is bigger than that. As soon as they remain, these are partial remainders, by the way. This is the first, wait a minute. Yeah, this is the first remainder, second remainder. But notice that the remainders are still larger. So x cubed is bigger than x squared. X squared, x squared is not bigger, but it is the same size as x squared. So we still continue. Not until we get a polynomial that is smaller, strictly smaller than this one that we divide by. Not until we get to that point, we finish. Okay. Now, how do we write the answer varies in the kind of problem we are given. You know, it's like if I tell, if we have this problem, so let's make an example out of this. What is something we cannot really split? Okay, so let's say there's 3 boats. Just this is a silly example. So there's sailboat, and sailboat, and then there is 13 people to put in the boats. So we do, and so how many people should be in the boats? Well, of course, we do 13 divided by 3. That gives us 4. 4 times 3 is 12. Subtract, and we end up with 1. So this tells us that we have to put 4 people here, 4 people, 4 people, 4 people. And then there is going to be one who's not going to go in the boat ride. Okay, because let's assume we want it to be exactly the even, an exactly even number of people. So the remainder, I know this is a silly example, but the remainder is 1, which means if we want exactly the same number of people, yeah, that's the other way to put it. Let's pretend we have a race or something like that. And whatever the number was, we want exactly the same number. Well, one person is going to be not going in the boat ride. Okay. Now, don't confuse this example with example 3. Okay. Let's say you have 13 apples and 3 people. So we're going to distribute the 13 apples to 3 people. Okay. So same kind of problem. And then you see, well, we did a division here, but this is a different problem. How many apples should each person get? Well, each person is going to be, so there's 1 person, 2, 3. So each person is going to have 1, 2, 3, 4 apples, 1, 2, 3, 4 apples, 1, 2, 3, 4 apples. But then we can take a knife and we can split that last apple that is left over and give 1/3 of the apple. So whatever that is, 1/3. I know this is a kind of a silly, that doesn't look too much like a third, but pretend that it's a third. Because one of the people are going to say, I don't need that third. The other person can keep it. You know, and if 2 people say that, then but let's pretend they have to have exactly the same amount. You cannot have one person with more or less than the other. Well, in that case, you can easily take a knife and cut the apple into 3, really, you know, carefully, and then you give each person 1/3 of an apple, and now everybody's has exactly the same amount, and then we're good. But here with the boat, we're not gonna split a person. You know, that's no, we are not gonna do that. That doesn't make sense. But with the apple, yeah, you can take a knife on. So which is the answer? Is it 4 and 1 left over, or is it 4 and a third? It depends how we ask the question. It really depends how we ask the question. I can see myself given a multiple choice problem where I'm going to give as a, what is the, if I ask, what is the quotient, assuming that there is a remainder left over, well, the answer is going to be 4. But if I say, okay, divide, what is the answer? Then the answer is going to be 4 and 1/3. So I can easily see, there's two different answers depending on how we ask the question. What is the quotient? 4. And then there's a 1 left over. As opposed to what is the fraction? What does the fraction boil down to? 4 and 1/3. Of dividing third. So there is the 13/3. There we go. Is equal to 4 and 1/3. So if we ask to simplify this by using division, there is the answer. If we ask to divide and to give a quotient, that would be it. But then there's a remainder. So please watch out, because those are two different questions, and we want to pay close attention to that. So going back to example 1, back to example 1. Okay, so if we say, okay, what is x to the 4? Let's go back to this, x to the 4 minus 2x cubed minus 2x cubed minus 11x plus 36, and divide that by x squared plus 2x plus 3. So that's the same thing. So if this is the question, simplify this, then the answer should be x squared minus 4x plus 5. I'm going to write down the answer here because it's not going to fit too well in there. So it's going to be x squared minus 4x plus 5. But then we have to have an equation, which means this fraction has to be equal to this, just like the 13/3. See, if I say 13/3 equals 4 without the 1/3, that's not true, because 13/3 is not just 4. If that was the case, 4 times 3 would give us back the 13, but 4 times 3 is 12. So no, we have to have 4 and 1/3. So this is like the 4, and how much is left over? In the negative 9 plus 21, negative 9 plus, whoops, I did the same thing again. I forgot the x. Negative 9x plus 21 divide by x squared plus 2x plus 3. So if the question kind of looks like this, then there's the answer. As opposed to versus something like, what is the quotient of x to the 4 minus, is that a 2? Yeah, 2. Minus 2 x cubed minus 11x plus 36 when divided by x squared plus 2x plus 3, question mark. In that case, the answer is just this guy, because quotient implies the remainder is not taken into account. So it would be x squared minus 4x plus 5. Yeah, and then there is a remainder left over. Okay, so be aware of that. Make sure you know how to divide polynomials. Practice division of polynomials. Practice, 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 practice. And then after that, then practice some more. Okay, let's stay with division of polynomials. If we are dividing polynomials, well, let's do one more example before we I was going to talk about synthetic division, but let's do one more example. Example 4. I'm going to start with the same polynomial, x to the 4 minus 2x cubed. This is the same polynomial. What I'm going to change is the divisor in this new example 4. But remember, we are going to give you this without the x squared, perhaps, or with one missing. If one of the exponents is missing, if one of the powers of x is missing after the biggest one, then fill it in with zeros. So I'm going to do that right away. There is no x squared, so we're going to put 0x squared minus 11x plus 36. And this time we're going to divide by something very, very, very simple. X minus 5. Okay. This is a very, very, very unique kind of factor. Remember in one of the previous videos when we were drawing the polynomials and we had like x minus 5, x minus 10, x minus 15. Those are very special factors. They're first degree, well, binomials. So they're first degree binomials, but there's more to it. The leading coefficient is 1. And that is very, very important. It's a very special kind of polynomial, these polynomials. If you have x minus 5 or x plus 5, x minus a number or x plus a number, or just x, those are very special. Anyway, let's divide. So, well, we got x cubed. And then we have, well, x to the 4 when we multiply, and then minus 5x cubed. And then we subtract as we did. So negative 2 plus 5 is 3x cubed, no x squared, minus 11x plus 36. If you don't want to write those here, you don't have to. Just remember they are there. So in the next step, they are taken into account. I don't like doing that because I forget them. If I don't see them, then I forget them. So I just as well write them down. 3, so that's a cube. So we need an x squared. 3x squared times x is 3x cubed as desired, so that when we subtract, they go away. But then there is another step here. 3 and 5 is 15, negative 15x squared. And that's it. There's only 2. We subtract. Those 2 go away. That was by design. And then we have 15 positive x squared minus 11x plus 36. See, those haven't been used yet. So that's why they could stay there. And not until there is a term that is underneath, then we can get rid of it. That's fine. I mean, we do that with the regular division. Actually, I didn't do that. I did bring the 0 and the 5 here. Then I don't know. I always bring them down. Maybe it's just me. Anyway, and then we have 15x plus 15x times x is 15x squared. And then minus 75 x, and then we subtract. So that goes away. Negative 11 plus 75. So 75 minus 11 is 64. 64x plus 36. We don't stop there yet because the degree of this polynomial is 1 and the degree of this polynomial is 1. We don't stop until the degree of whatever is left over is less than the degree of this. Now, if this polynomial has degree 1, we have to have a polynomial of degree 0, which is simply a constant, no x. So a polynomial of degree 0 means no x. Degree 1 means 1x. Degree 2 means 2x's, such as in x squared. That's what we mean by 2x's. 3x's, 4x's. Anyway, so now we match that with 64. 64 times x, 64x. 64 times 5 is 320 minus 320, but then we subtract, and that goes away. That is positive 320 plus 36, 356. So that is the remainder. That is the quotient and the remainder. There's a lot of information that is going on here. And so let's start with a few things. Okay, so we're gonna milk this example with a bunch of pieces of information. The first one is, let's say we have a p function of x, which is gonna be this polynomial, x to the 4 minus 2x cubed. There's no need to do that because we're not dividing. I'm just writing the polynomial. Minus 11x plus 36. Okay, so pretend you have a polynomial like that. Plug in 5. So that's going to be 5 to the 4 minus 2 times 5 cubed minus 11 times 5 plus 36. That is just numbers. 5 to the 4 is 5 times 5, 25, times 5, 125, times 5 is 625. So that is 625 minus 2 times 5 cubed. But 5 cubed is 125. We're going to figure this out in the next step. Minus 11 times 5 is 55 plus 36. Okay, we can probably start subtracting things. 625 minus 55, I think is 5. So there's, if we take 25, those 25, there's 30 left over. So that is 570. So those two subtracting together is 570. But then we're going to add 36. So we go back to 606. And then we're going to take away. So I did 625 minus 55 plus 36. And I got 606. I'll check in a moment. 2 times 125 is 250. So let's subtract those two. 6 minus 0, 6. 10 minus 5, 5. Because we borrowed a 1 from the 6. So now we got 5 minus 2, 3. So if we plug in 5 in this polynomial, we get 356, which is exactly the remainder of dividing that same polynomial by x minus 5. Isn't that wild? Yes, that is, and that is no coincidence. Every time we divide by x minus 5, any polynomial, you name it, if you divide by x minus 5, in long division, whatever the remainder is, that answer is going to be exactly the same answer as plugging in the 5 into the polynomial. And that is no coincidence. That is exactly true. Okay. Let's go to synthetic division. I'm going to make an example out of this, even though I'm going to use the same polynomial. Okay, so let's say divide x to the 4 minus 2x cubed minus 11x plus 36 by x minus 5. Okay, so it's essentially the same problem, but I'm going to show you a way to do this more effectively. It is called synthetic division. Okay, so first write down the coefficients of the polynomial. The polynomial has to be written in descending order from highest degree to lowest degree. Okay, so we are going to have 1, -2. Now, if you put -11 next, that's going to mess up your answer. And if I have a multiple choice question like this, I'm going to give the answer as one of the possible answers as the one you would have obtained if you kept the -11 as the next number. Okay. So no, but we are smarter than that. We're going to say, wait a minute, there is an x squared missing, so we're going to put a 0 for the x squared, -11, and then 36. So we got degree 4, degree 3, see, degree 3, degree 2 missing, degree 1, degree 0. We have to go from whatever the highest is down to degree 0. And all of them should be there. If there was no 36 here, nothing, then you put a 0 still there. Put the 5, so whatever this number is, this is, if we're subtracting 5, put a positive 5. Okay, so here's the method. You got to pay close attention to this. And you can rewind the video going back to how to do this. So the 1 goes down as is. 1 times 5, and then we multiply. 1, whatever this is, multiply by 5 and put it in the next column. Then add those numbers. 3, because -2 plus 5 is 3. Multiply with the 5. 5. No, 15. 3 times 5 is 15. Add those numbers. 15. Multiply with the 5 and put the answer in the next column. 75. Add those numbers. 64. Multiply with a 5. 320. Add those numbers. 356. The last number is the remainder. Furthermore, those are the coefficients of the quotient. The quotient will be, okay, if this was degree 4, if we started with degree 4, this is the coefficient of degree 4. This is going to be a coefficient of degree 3. And then it goes down from there. So we will have, as the quotient, will be x cubed plus 3x squared plus 15x squared plus 64. Now let's double check because we did this problem in example 4. Here it is, example 4. X cubed plus 3x squared plus 15x. Oh, I made a mistake. I put x squared twice. Okay, so we go 3, 2, 1, nothing, no x. Yep, and that matches beautifully. So this table is way easier than this long division. And it is the same. We got the same quotient and the same remainder. Yep. There's a catch. The only time we may use long division is absolutely, exclusively, is if we have, so I didn't finish my sentence, sorry about that, but I want to write it down. So So we may use synthetic. That's what I meant to say. I forgot what I said, if it was synthetic or long division, but I meant to say synthetic. We may use synthetic division exclusively when dividing by x plus a number or x minus a number. This symbol may represent a number. That symbol can mean several things. So again, this is a number. It can also mean pound or pound. It is actually called the pound symbol. It usually means a number. So x plus a number, x minus a number. And the reason I'm not trying to be condescending. Please forgive me if I come across as condescending when I'm explaining that. But the reason is because my daughter, I don't know, months ago, she was on the phone and she had to type the pound symbol, and she asked me, "Wait, is that a hashtag symbol?" And then I thought, oh, I guess not everybody remember, because maybe that's an old symbol with pound and number, and now people use it as a hashtag. So again, please forgive me. I'm not trying to be condescending or anything. I just, my own experience, my own daughter was doubtful of whether uh, this should, what this was. She probably knew, but she wasn't positive. So anyway, um, division, synthetic division, practice synthetic division. Oh, and the neat thing about synthetic division is that sometimes doing those computations are faster. If you want to find um, an output of a polynomial, the synthetic division quite often is faster if you're doing it by hand than actually plugging the number. So for instance, back here, we had to come up with 625 and 250, and then we have to do a bunch of additions and subtractions. Here, we never got to 625. Isn't that neat? We never ever did. And yet we got the same answer. So synthetic division can be simpler than plugging in the number. And that's why many times it is preferred when we are plugging in a number to get an, when we plug in a number, yeah, the synthetic division can be easier. So that was example 5. Example 6, I'm going to check my notes real quick to see. Yeah, the next thing we want to cover is how to build polynomials. So building polynomials. Okay, say we ask you to put together a polynomial of degree, okay, so build a polynomial of degree 3 with zeros 3, 2, and -1. Okay. So what we have to do is, so let's say P of X. So that's the end of the question. How do we do this? It's not that hard. Just do X minus 3, because if 3 is a 0, then X minus 3 has to be a factor of the polynomial. Also, X minus 2 and X. Technically speaking, we should have X minus -1. So we always have X minus whatever the number is. X minus 3, X minus 2, X minus -1. So there it is. That's the polynomial with those zeros. And then we typically will ask to FOIL that out, to multiply it out. So multiplying those two will give us x squared minus 5x plus 6, and then multiply by x plus 1. And then that's going to give us x cubed. Well, I'm going to multiply now x with those, so x cubed minus 5x squared plus 6x. So the x got to be multiplied with those, but then we multiply the 1 with all of those, plus x squared minus 5x plus 6. So that is x cubed. And now we got to simplify. We got negative 5 plus 1 of the x squared. So that is minus 4x squared. 6x minus 5x is x, and then 6. So there is our polynomial of degree 3 with zeros 3, 2, negative 1. 7. Build a polynomial of degree 3 with zeros 3 and 2. So instead of providing 3 numbers, now we got 2 numbers. But we want the degree to still be 3. We have 2 choices, and only 2 choices. Okay, so the polynomial has to be x minus 3. Well, it has to have x minus 3 and has to have x minus 2. But wait, we need a degree 3 polynomial, so that means we need to have 3 factors. But I cannot really put any other factor that is different than those 2, because then that would lead to another 0. But we have to have those zeros and only those zeros. So maybe I can be more narrow on this question. Build a polynomial of degree 3 with only zeros. With only zeros, 3 and 2. That's it. No other zeros. So it looks like we have sort of a contradiction. How are we going to get 3x's when we got only 2? Very easy. Double up on one of them. So just double 1 on this one. But somebody could say, wait a minute, can I double up on the other one? Sure. So there's 2 possible answers. Or, technically speaking, there are many answers, but I don't, because we can multiply with an arbitrary non-zero constant, and that will generate any other polynomial. But let's pretend we want to stick with x cubed. What I mean by that, with 1 as the coefficient. Or p of x. So if some students write this out, and you guys still have to multiply it out, you're good. If some other student says, hey, I'm going to do x minus 3 and x minus 2 squared, that's fine, because there's no other restrictions on the problem. So if half of my students do this and the other half of my students do that, they're both going to be correct. Yeah, the way I would probably ask the question would be, if I was to ask this question on a multiple choice problem, is which one is not a polynomial of degree 3 that has only those 2? So I would probably put those 2 down, and then maybe a third one that is not going to work. Yeah. Yeah. What if we ask, okay, so 8, let's see if I can squeeze it here, build a polynomial of degree 3 with the only, excuse me, the only 0, 2. So just the 2. Okay, so the only factor we may have is x minus 2. That's it, no other factor. But we want the polynomial to be of degree 3. All you have to do is cube it. And then you're all set. Well, We might have to multiply it out, FOIL it out, and all that, but that's about it. And then there is one other example I would like to provide. 9. Okay, so build a polynomial with real coefficients, and with zeros, 3 and 2 plus I. Okay. So that is a complication. The 2 plus I is a complication, but I'm going to show you how to handle the complication. So we're going to have x minus 3 for sure. We're going to have x minus the number 2 plus I. But if we want to end up with real coefficients, the I should not show up in the polynomial. And there's one way to fix that. We have to include the conjugate. So if you have 2 plus I as a root, and we want to end up with real coefficients, the conjugate has to be included. I'm running out of room, and I want to put them all together, so I'm going to disregard that. I'm just going to rewrite it down here because I wasn't planning my spacing well. So x minus 3, x minus quantity 2 plus I, and then x minus quantity, what is the conjugate of 2 plus I? 2 minus I. And we got to multiply that out. Practice that. Let's multiply it out. Well, I advise against multiplying with x minus 3 first. What I do, and every time I'm working out a problem like this, I multiply the 2 with the complex numbers first. And then I multiply by x minus 3 last. Otherwise, you have too many i's floating around and I squareds through the whole multiplication. If we multiply those two at the beginning, yes, there's going to be i's and I squareds, but they're going to be gone as soon as we multiply those two, and then we don't have to worry about i's anymore. Okay, so let's multiply x, distribute the negative, so we have minus 2 minus I. Minus 2 minus I, and we're going to, so I'm not saying that this is equal to what I'm writing here. I'm just doing those two and multiplying them together. X minus 2, distribute the negative, plus I. Okay, so x times x, x squared. X times negative 2, negative 2x. X times I plus ix. Okay, so the x is done. Negative 2 times x, negative 2x. Negative 2 times negative 2, plus 4. Negative 2 times I, negative 2I. Okay, the negative 2 is done. Negative I times x. I'm going to continue down here. Minus ix. Negative I times negative 2, plus 2I. Negative I times I, negative I squared. Now, some of you will be thinking, can I do that in a box? You know, there's a box and then you put some on the row. On the first row, you put this, and on the column, you do this, and then you multiply. Fine. Yeah, that is perfectly good. As long as we don't make mistakes doing that, we're good. So x squared, there's only one. Minus 2x, minus 2x. Okay, so that's minus 4x. And notice that ix minus ix are going to cancel off. In fact, negative 2i plus 2i are going to cancel off. So those are gone. what is left? 4. And then I squared is really -1. Just the I squared is -1. But then we have an extra negative in front. So that is +1. So we have x squared minus 4x plus 5. Okay. So this polynomial has complex zeros, 2 plus I and 2 minus I. Now that's not the answer yet. The polynomial is x minus 3 times those two, but we just figure out that the product of those two is x squared minus 4x plus 5. So p of x is x minus 3 times x squared minus 4x plus 5. And then we multiply. So I'm going to multiply the x with that, x cubed minus 4x squared plus 5x. -3 times that, minus 3x squared plus 12x minus 15. So the answer will be x cubed minus 7x squared plus 17x minus 15. And there it is. It's the same. The reason why I put it down here is because I want to box it. There is the answer to problem number or example number 9. Practice, practice, practice. Math is really about practice. We cannot do math without practicing. Maybe we could, but I don't know how. It really, most people have to practice a lot in order to understand math. And with this, we're gonna close this video.